Hello everyone, we are back and we are going to our beam bending problem. So let's look at our problem that we're working with. So get rid of this, let's get to our beam bend. We are working with a ceramic material, so we can change that to 300 gigapascals. Forget about this load. My width is going to be 765 millimeters. My thickness will be 0.5 centimeters. And my length will be 5,000 times 10 to the minus 3. And we can set our function as a positive 10 times 10 to the 3 Dirac delta of x minus L divided by 3. And then minus 1 times Dirac delta of x minus L divided by 4. Let's see here. Oops. Let's get that. No. 765 times 10 to the minus 3. Good. All right. So what are our boundary conditions? Well, at y of 0, 0. That's correct. At y prime of 0, it should be 0. And we can copy and paste these for L. So symmetric boundary conditions. So we can do y of L is 0 and y prime of L is 0. So those will be our boundary conditions. We can solve our function. And now let's see what we should expect it to be kind of bowing up a little bit. Let's get our solution. X from 0 to L. And this makes quite a bit of sense. So where does the maximum displacement occur? So instead of find minimum, we're going to do find maximum. And let's start at, let's help it out. X of 2. 2.1 looks pretty good. So that's our value for our maximum displacement. Where it occurs along the beam is right here, maximum value, very similar. By happenstance, not by there's a design at all. If we want to find our maximum bending, we're going to look here. So let's say find maximum. So we can set that equal to our expression for stress is equal to minus our moment, which is positive here. Why is it positive? Let's look at it. Actually, that's what we calculate here. But the bending moment is positive. Kind of makes sense because we're looking at like a little bit of a positive curvature there. But anyways, we'll get to that in a second. So when we plug this in, that actually makes sense because top half should be in compression looking at our deflection. Good. That's our value. So where does maximum stress occur? So we did this. We found the value. Beam has initial crack of this. Will it fracture? This particular ceramic has a surface tension of this and this. We can't use strain energy release rate, so we have to use our Griffith criteria, which is going to be square root of 2 gamma E over pi A. And we were already given that initial crack length, so we need to solve for what is sig F set equal to square root of 2 times gamma, which is 85, times our Young's modulus divided by pi times 6 times 10 to the minus 6. Let's solve that numerically. Let's see if it compares. Ooh, pretty close. Pretty close in value, but this is actually higher, so definitely will fracture. That beam is a goner. So, there are 3 viscoelastic materials below. X-axis is strain rate. Determine which symbol correlates to storage and loss modulus, which is most solid, which is most liquid. So, high strain rate, which would be here, means that we need to act like a solid. So, empty is my G prime. Very, very low strain rate. Filled is our G double prime. And we can see that we have to pull let's see where the crossover points are. Crossover points are here, here, and black. Actually, black about right here. So it's pretty close for the most viscous, but it's definitely clear where I don't have to pull that fast to be solid. So red is most solid, and we've got it for the other values. So, excellent. We will see you all in the next video. Thanks. Bye.